Hi, everyone. Welcome and thank you so much for being here. I hope you're having fun exploring our Lens Studio capabilities and working on your hackathon project so far. My name is Zargeta. I'm a technical program manager at Snap, and I'm here to tell you a little bit about SnapML and how to use it for your hackathon creations. Specifically, what I'd like to cover in today's session is an introduction to SnapML, explaining some of the differences between using the ML templates versus bringing in your own model. And then we'll move on to a live exercise where I'll show you how to set up an ML model on Google Colab, all the way to the steps of prepping and deploying the model for Lens Studio consumption and a quick setup for an ML lens. But before we start, I do want to say that if you haven't signed up yet, I encourage you to sign up for the Lensathon on the Snap Lens, lensathon.devpost.com. I encourage you all to work on this hackathon with us. So what is SnapML? SnapML is a feature of Lens Studio that essentially enables you to bring in your own machine learning models to build AR experiences. So it's catered towards machine learning developers who have their own ML cases that they want to bring into the platform, but it also enables AR developers to get started with SnapML by providing some model templates that we'll be talking about in a little bit. And the goal of SnapML is to democratize machine learning and open it up to as many people as possible to do what they're interested in. So like I mentioned, we do provide some starter templates for developers who are interested in jumping right into develop AR experiences. And these templates serve as a starting point and offer some of the more core functionalities that you would expect from machine learning models. And here's a list of these templates and the capabilities that we currently provide on SnapML that you can get started with today. The items that you see on the left are templates for which we provide training code. And training code is great if you're really looking to tweak the existing models and either add your own data set or swap the model altogether. It essentially is there to help guide you through the training process that is required to make your model work. An important thing to remember is that for SnapML is that there's two ways that you can get started. First one is to use one of our existing templates and models. This essentially means that you do not need to train a model from scratch to be able to use SnapML. We've already done that work for you. And if your AR use case benefits from what's already available with SnapML, then great, you can go ahead and get started with those templates. And your real work there really starts when you import that model into Lens Studio and then you kick off your AR development process. However, if you're looking to develop an AR use case for which you need a custom model that you yourself train on a specific object or scenario, for example, you want to identify sharks, then you can bring in your own model that is trained to identify sharks. Now I would like to walk you through the bird's eye view of the SnapML workflow from beginning to end. Every project for SnapML starts in one of two ways. You either build your own model or you start with one of the templates. If you're using one of the templates, you can skip this part and go straight to Lens Studio. But if you're training your own model from scratch, what you need to get started with is your data set and your training code. And we usually recommend using Google Colab as a way to get started, but you may also use other tools as well. As you're training the model, it's important to check the model's compatibility with SnapML. And you can do that by accessing our compatibility sheet on the Lens Studio documentation. It's worthy to point out that SnapML optimizes model running, leveraging hardware acceleration. And next step is exporting your model into Lens Studio. We support some of the ML open formats, such as Onyx and TF-Lite. And before bringing your model into Lens Studio, you do need to convert it into one of these formats so Lens Studio is able to recognize it. And once your model is done, you can simply drag and drop it into Lens Studio and set up the ML component. With the ML component set up, then you can configure your model inputs and outputs, and then you can also trigger further events to happen that can personalize your AR experience. So finally, once you've done all of this customization, it's the deployment phase. This is the time where you can preview your lens, you check your model performance, and then you launch it according to our community principles. Now that we have a general sense of the overall SnapML workflow, I do want to shift gears and focus the rest of this workshop on walking you through how to set up a simple image classification model with SnapML as well as Lens Studio. And for simplicity, we'll go over a very famous example of the model that identifies cats versus dogs, kind of like a classical ML use case. And for this exercise, we'll be using Google Colab to set up our training notebook. Step number 1 includes enabling GPU on your notebook. And the way to do that is by navigating in the edit section, go to notebook settings, and then selecting GPU as hardware accelerator. The main reason we do this is to run parallel processing, which makes our training process faster. Once you set up your GPU, then we are all set up to work on our PyTorch dependencies. So PyTorch is a well-known ML framework that is used to train powerful ML models. So here we're essentially importing functions and capabilities from Torch Vision. Torch Vision is an auxiliary library from PyTorch that provides a lot of helper functions and utilities for computer vision tasks. And then you finally run CUDA. This is so you want to check if you have an NVIDIA GPU available for usage. And then the other step before we go into the notebook directly is that you also want to set up a Kaggle account. Kaggle account in our case will be used so that we can retrieve a data set for our model training example. You may use obviously other data sets as you wish. You can also build your own data sets. Just for the purpose of this one, we'll go with Kaggle. So the first step would be register a free account with Kaggle on their website. And then once you have your account set up, you should be good to go. So we're going to switch gears here, and I'm going to go directly into our notebook that I've set up that we will be sharing. So we're ready to go into ML model development mode. And essentially, if you think about a typical ML model pipeline, it goes as follows. It starts with the data set that you're going to be using to train the model. Then you're setting up the data pipeline that will feed into the model that you're building. And then you're developing and training the model. And then you're evaluating the model results. So we'll start by looking at data sets, which are one of the most important components of developing an ML model, because that's how the model learns from to begin with. So depending on the ML use case, you may need to use specific data sets to do the job. But if you're getting really just started with ML, open source data sets are typically a very good way to get started. So in this exercise that we're going to be working on, we're at the stage where we need to connect our Kaggle API so we can get access to the data sets that are available over there. So when you go into your Kaggle API account, there's an API section through which you can download the API token, and that will be downloaded as a Kaggle.json file on your computer. Make sure to locate it where it is. Then you'll run the following code to be able to upload that model into your Google Colab. So when you run this cell, it's going to prompt you to choose that file from wherever it is locally saved in your computer. And then once you're importing it, just make sure that the file is there, and then you should be good to go. Now it's time to start looking into the data set. So before we do that, we want to kick off our Kaggle API client by doing a pip install of Kaggle, making sure that our API key file is moved to the Kaggle API client folder. And then there's an important step here, which is you want to make sure that you are changing the permissions to avoid a warning on the Kaggle tool startup. And then once you do that step, you should be able to explore the data set. And as I mentioned, we'll do the classical cat versus dog data set. So we can start this exploration by looking at data sets that might have cats in them. There's a whole list of it if you just run this script that I wrote over here. We pick one that is that has a reasonable amount of data in it. We download that data set, and then we unzip it, and then we're ready to go. So then we go into data set exploration, which essentially ensures that we have a good sense of what the data set that we're going to be working with looks like. And this is an important step because the quality of the data that you're inputting into your model will very much determine the quality and the accuracy of the model that you end up building. So we can start this process by taking a look at the folder structure that the data set comes with. In this case, the cats and dogs data set has the training and testing data folder specified for every class, which is pretty neat. It does make our job much easier. Usually it's not the case, but with cleaner data sets, that's usually kind of like an easier way for developers to get started. And then I always highly recommend folks to do a quick visualization using Matplotlib, which is a visualization library that essentially it can show you your data set at a very itemized level. And this is basically just to kind of like get a sense for like what kind of images you're actually seeing in your data set. In this case, we're seeing a dog. It's great. It's supposed to be one of our classes. So this is good news. So in machine learning, to be able to train and evaluate a model, it's important to split up our data set into train, validation, and test sets. And this way we can use the training data to train the model, and then the validation and the test data set to see if our model has overfitted from the training data, or if it's actually learned interesting patterns from it. We don't want it to be memorizing data. So for our example, just to make it more simple, we'll split the data into training and test set. Fortunately for us, the dataset developers already done the work for us, but if that wasn't the case, then we would want to do the split ourselves. And usually we recommend a split between 80-20, 90-10, depending on the use case. And here's some code that basically allows you to look at the number of samples on each class of the training and test data set. And what we see here is that for both the class, for cats and for dogs, you're seeing a 75 to 25 split. So now we'll go through our data pipeline. This step, basically what it does is that it's converting our raw JPEG images from the data set into tensors that are consumable by PyTorch. So first we want to set up some parameters. The first one is the center crop size. This essentially defines our input image size. In our case, we'll use a 224 by 224 pixel image. You can use other pixel sizes for image inputs as well. Just be aware that computational costs may arise if you pick larger image sizes. Then we'll define our training and validation directory, or in our case, the test directory. And then we'll also define our normalization parameters. Now, when you read raw JPEG in, it'll be converted into a NumPy array. So sometimes it can be between 0 to 1, or 0 to 255, but for the model to work best, we want something that normalizes well. So usually that means normalizing around a 0 mean and 1 standard deviation. So this process is quite important because if you don't normalize your data, sometimes some of the axes will have higher standard deviation, some of them will have lower standard deviation, and it's going to be very hard for the network to learn from this data. So normalization takes care of that. And in our case, the normalization parameters are taken from the ImageNet data set, and this will come in handy when we start training the model in just a little bit. Next, we look into the TorchVision dataset.image folder from the TorchVision library. This TorchVision library provides a very useful model that reads the classes of the folders for the image data set that you care about. So it reads that data set directly, passes the folder path. It's also able to transform. And then this is where we do our data augmentation and normalization pipeline. So there's a few sort of like terms here, things such as random resize crop, random horizontal flip. So the flip mirrors the image, whereas the random resize crop first resizes the image and then randomly crops it. So every time we go through the training loop, the model is able to see a different image, even though we're using the same data set. And what this is doing is that by not seeing the same image, the model is less likely to memorize the data and not learn patterns. So we're essentially enhancing and augmenting the data set that we're working with. I do want to point out that data augmentation only happens in training data set. So we don't need to do that for the validation or the testing set. So in here, we're just resizing and doing center crop for our normalization piece. So this is kind of like a visual example of what those two components that I mentioned, the random resize crop and the random flip look, actually think about it from a visual standpoint. Then we are ready to set up the data loader. So the data loader is a PyTorch module that helps us batch our image tensors, and it transfers them to GPU more efficiently. So if we don't use a data loader, think of it as like we'll be training directly the data set from in Python. and we won't be able to leverage the parallelization that comes with GPU processing. So you will essentially have one single thread, which will take forever to happen. So in our case, we'll batch our 64 images together, and then we'll transfer it from CPU to GPU. And then here we pass our training data set, the batch size. We turn shuffle on, which will randomize the data set order every time we go through the data set on every epoch. So this helps with model generalization. And then number of workers is how many parallel threads you want the model to go through. For this one, we'll use 2. It's kind of like the bare minimum, but you can change that according to how much robustness you want. And then finally, pin memory is a flag that makes your data processing slightly faster. So we set that up to true. Then we set up some quick model performance metrics. This is just a bunch of progress bar helper utility functions, essentially, that will help you understand how your model is doing as you're training it. So now we're ready to go to the model part. And today we'll be using MobileNet v3, which is a lighter and faster model architecture. What's an interesting fact about MobileNet v3 is that it's actually partially designed by a machine, and it has produced superior accuracy with lower computation. Now, something to point out, the default MobileNet v3 will not work in SnapML because of some unsupported operators, which include hard sigmoid and hard switch. So what we'll do is we'll do a little bit of a model surgery where we will swap out these models to make it compatible without impacting the performance of the model by too much. So first, we set up the pre-trained to false. This essentially means that we're not using any pre-trained parameters from ImageNet, which is where we took the normalization parameters from. And for this first iteration, we won't be using it. And then we use Torch Vision to import the pre-trained MobileNet v3 model in, and then we're creating 2 helper functions that will replace the hard sigmoid and hard switch activations with something that is currently supported in SnapML, just like I mentioned before. And then in the next steps, because our data set has 2 classes, whereas the default model that is trained on ImageNet dataset has 1,000 classes, we want to configure our current data set by swapping out the final classifier with outputs equal to, in our case, cats versus dogs. And we do it so that the model is able to basically output things that we care about. And then finally, you want to modify the dropout layer to false, since we've changed hard switch with ReLU, and that is because 2 consecutive in-place operators are not allowed in PyTorch. Next, we want to work on the loss function. The loss function is the feedback mechanism of the model. So you want to minimize your loss function in any kind of ML model that you're building. Now, we're not going to go into too much detail about the loss function, purely because it's just mostly math, but you can look it up. It's called cross-entropy loss, and there's a mathematical explanation behind it. But what we do here in this line of code is we're essentially moving this function into GPU. Next is the optimizer. So optimizer is used for tuning our model hyperparameters to minimize the loss function. So we'll be using, for this exercise, the stochastic gradient descent algorithm as an optimizer. It's usually abbreviated to SGD. We have a couple of hyperparameters to set. The first one is the learning rate. The learning rate, what it does is it controls how much to change the model in response to the estimated error every time the model weights are updated. So figuring out the learning rate is tricky because too small of a step may make the model get stuck in training, and too big of a learning rate can cause instabilities, and basically it's changing the model weights too fast. A good example of how to think about the learning rate is, think of it as a valley, where if you're taking a very big step, you're essentially skipping parts of the valleys. Whereas if you're taking very small of a step, you're basically not able to see where the next step is coming. So in this exercise, we'll use a learning rate of 0.02. That's something that you may need to tune as you keep training your models. The other parameter is weight decay. Weight decay is essentially a penalty parameter that ensures that the model weights are not super large, which could lead to overfitting. And this value over here tends to work well for most computer vision use cases, but again, it's something that you have to kind of play with. So now you can set up now essentially you're ready to set up your optimizer with the stochastic gradient descent algorithm. Then we can set up a checkpoint, which essentially saves your model states in case the model fails as it's training. So essentially, this is a safety guardrail. As your model trains, you can resume it if it stops. Next, we want to define our validation loop. Validation loop will check the model performance on unseen data. If the accuracy of the model decreases as we train, it may indicate that the model is overfitting. So what we want to do is that we want to switch our model into evaluation. And this is important because you don't want to switch some of the layers that are not going to be working correctly. So in our case, the batch normalization layer and then the dropout layer. And then with torch no grad, what this does is it turns off the gradient calculation process, which can help you save computation costs. And then we also want to record how fast we're going with validation. We then pass the image into our model and get the output. We compute the loss function as well as some metrics. The training loop is very similar to validation loop. The only difference here is that we switch to train mode, and then we'll also print the learning rates per epoch. And in the training process, we'll gradually decrease the learning rate to help the model converge. And then the other additional part for the training loop is that we add a zero grad because PyTorch doesn't automatically clear your gradient buffer, so we have to manually add it. And if we don't do this, the gradient will continually getting bigger and accumulated. So then we also add loss backward that uses back propagation algorithm to compute the gradient. Once you compute the gradient, you then use your optimizer to change the parameters in optimizer step. And then we also have the learning rate scheduler that changes the learning rate as we go, like I mentioned. I want to note that both validation and training loop go through the data set once. And in training, we want to make sure that it goes through the data set multiple times in order to learn more efficiently. So here we have the learning rate scheduler set up that is imported and provided by PyTorch. Then we put our model through GPU, making sure that the learning rate is set up correctly, and then we train on 10 epochs. You can increase the number of epochs if you want. That's totally up to you, and usually that can lead to improved models. Then you can also set up some bookkeeping items to keep track of the model, of the metrics as the model keeps training. And then once you have this set up and run, what you'll see is that you'll start getting some accuracy metrics across all the epochs alongside with how the loss function is performing. So since we set up 10 epochs, you'll see that there's 10 epochs that are being trained. And then you see that we have an accuracy of the initial model that we trained at about 82%. On the second training iteration, now what we did in the first iteration was that we actually trained the model from scratch. On the second training iteration, we'll use pre-trained weights from ImageNet to hopefully get better results. So this example is the same code, except for the part where the pre-trained flag is set up as true. And that basically means that we're using the weights that are coming from the ImageNet pre-trained MobileNet v3. So when you run this block of code, you go through the same process. It's going to iterate through all the epochs. And as you can see at the end, you'll see that the accuracy that we've achieved by using pre-trained weights is 96, which is better than the first one. So it's important to note that even though we swapped some modules here, the ImageNet pre-trained weights prove to be very helpful and useful because they're very robust in terms of improving our model accuracy. So now that we've trained the model, it's time to test out some of its results. And an easy way to do that is to simply visualize the model. So what this is doing is this code is taking in it reads the image, converts the tensors to a prediction, and then it returns the results. So here's an example of what it looks like with two test images. These are images that are taken from our test data set. This is the data that the model has not seen yet. So what it is doing here is that based on the order of these classes, in our case, 0 is cat and dog is 1. You see that the tensor gets picked based on the highest probability of the case being a cat. So in this first one, this is the highest number, it's picking cat. This is for the second one, this is the highest number, it's picking 1, which is dog. So the model is essentially predicting these correctly. Another great and very powerful way to visualize how your model has done on the entire test data set is to build a confusion matrix. So the confusion matrix essentially visualizes the number of instances that the model got right and wrong across all the possible classes. So the diagonal, the yellow classes or the yellow boxes indicate the correct predictions, and the blue ones indicate the wrong ones. And the true label is the ground truth, or the actual class of the image that is predetermined. Whereas the predicted label is what the model recognized as the class. So with having covered confusion matrices, this essentially wraps up the model development component of an ML pipeline. So now we're ready to get this model exported into Lens Studio so that we can continue the development of our ML lenses. However, before we start doing that, and I mentioned it a little bit at the beginning of the presentation, it's important to note that we can't just simply download the PyTorch model in and import it into SnapML. It'll not allow us to do that. However, we'll need to convert that model into an Onyx file. So what we do is we first wrap our models within a softmax activation to be able to get the probability outputs of our model. And then we create dummy images. We set input and output names to reference in SnapML. And this is so that the Onyx utility is able to trace the entire graph. And then we use the Onyx helper function to export it. And then we download the file. And I've already done that for this exercise to get ahead of it. But with exporting the model, what this basically means is that now we're ready to move on to Lens Studio. So the first thing we're going to do is go to the objects panel and then pull up an ML component. And what we're going to do in the ML component is we're going to be importing our MobileNet v3 model that we just exported through our Google Colab. So what you'll see as you import the model is that the model import table comes up. And here what we'll do is we'll configure the inputs based on our model. So here we need to set up our channel scale and bias parameters. What we do in SnapML Lens Studio documentation is that we actually provide you a formula to be able to calculate the scale and bias for your model. In this case, we've used that formula and we've calculated them. So what I'm going to do is I'm going to simply copy and paste them from our Google Colab. You'll have access to this after the presentation. But essentially, I'm adding the calculated scales and biases that are coming from the normalization parameters that we've calculated. So I'm going to do that really quickly. And then we're going to add the same values for the bias that we've calculated. 2 more. So these are the inputted scale and bias values for the channels. Then what we also want to do is we want to make sure that stretch is set up to false. So we unclick this. Basically, this is an input transformer setting. When we enable stretch, the texture is stretched to the size of the model input, but we don't really want that. So we unclick. And once we do this, we can click import, and that will get us out of the model import UI. And now we've imported our model in. Next, what we do is we come here in the inspector tab of the ML component, and then we set the texture to device camera texture. And what this will do is that it will feed the camera input into your model. Next, what we want to do is we want to be able to display the model results onto the screen. So what we do is we go into the object tab, and then we add a screen text. Then what we're also going to do is we'll go into objects. we're gonna go into helper function, helper scripts, and then we'll select and we'll add a behavior script. And we'll keep it here for now. We'll go back to the behavior script in just a second, and I'll explain what it's doing. Before we go into behavior script, we want to be able to add the script that will enable the model to run, as well as generate the model predictions and outputs. So what we're going to do is we're going to go into resources. We're going to click the plus button, and we're going to add a script. So the script, then we double click on the script, what we're essentially going to do is I have a script that I've pre-prepared that I'm going to add to this file over here. And I'll walk you through what that script is actually doing. So let's copy that here. So what we're essentially doing as a walkthrough of this script is that we're establishing the inputs which hold the information that we need. And we're also adding the ML component that we care about, as well as the screen text. So these are all the components that we care for the experience. Then we want our ML model in the ML component to run. So we create an event whenever there is a model update. Now we also want to set up a function that will be able to provide us with the model outputs. So the function get output waits for the ML component to load before running the function. And then once loading is finished, the function runs by retrieving the results of the model in probability form. In the array, it compares the results between both classes, which as a probability should equal to 1. And then it assigns the highest probability number to the corresponding class, which in our case is either a cat or a dog. So it's then printing the probability and the index value associated with it. So on the screen here, once we actually try it out with a couple of example images, you'll see the assigned class according to the index value printed as a cat or dog, depending on the input. Now I don't have a cat or a dog in real life, so we'll test it out with a couple of images that I've downloaded. So we'll try and do that through here. So we'll be importing a cat. Now that we have the script set up, and I kind of walked you through what that looks like, we're going to go back to the scene object of the behavior script that we put together. So what we're going to do here is that we're going to select our script from the behavior list, and then we're going to run that on awake. So the model is generating outputs anytime that there's an input that is coming in. And we're going to set up our ML component with the ML component that we have for the model, as well as the screen text that we created just before. So that should essentially give us all that we need to be able to test this out. What I've done here is that I've added I don't have a cat or a dog in real life. So what I've done is I've added a cat image just to kind of like show you what those outputs looks like. So once you input this cat image, then the model is generating the cat result. It's associating the highest probability, indexing it with the correct class that it's able to identify. And we can do the same thing with the dog, with the dog image. And as you can see here, the model was able to run. It's giving you the probability of 99% it's a dog, and then it's also providing you the index of the class, which is dog. So that concludes our session for today. I hope that you learned something and that you get to experiment with SnapML during your time in the hackathon. If you have any questions for us, please don't hesitate to reach out. And we also have plenty of documentation that you can look at to get you started, as well as a GitHub repository with training code if you want to have a quick and fast way to get started. As a reminder, we'll be sharing this documentation as well as the walkthrough that I showed you on Google Colab today. So keep an eye on that very soon. If you have any further questions during the session, we're more than happy to take them now. So feel free to drop in your questions in the Q&A session and section, and we're happy to walk through them together. Thank you. All right. Let's take a look at the questions that we have over here. I'm just realizing I'm really sorry that you guys were not able to see the presentation clearly, but I promise you, we will be sending out the Lens Studio, the Lens Studio project, the presentation, as well as the Google Colab walkthrough after this. Let's quickly go through these questions real quick. If you show it a picture of a washing machine, will it give a higher probability of a cat or a dog? So in this case, the model was actually set up to only identify cats versus dogs. So anything that is not a cat or a dog, it will unfortunately trigger it to provide one of those probabilities. But what you can do to actually mitigate for that is that you can add an other class into your model. So when you're training it, you're essentially training it with 3 classes, and anything that is not a cat or a dog from a probability standpoint, then it's gonna default to other. So as part of your training process, what you can do is you can add the other class or the other category, and then add some more images into your training data set that is not cats or dogs, and that should take care of it. Any other questions? For those who are just starting with ML, do you have good starting material like existing models or data sets? Yes, we do. So we will be sharing that as well with you, but I can actually provide you a link right now, and we'll make sure to add that into the documentation afterwards. But we do have a GitHub repository with some of our SnapML templates. These are sort of like complementary to the templates that we provide on Lens Studio. And it's a great way for you to get started if you're just getting started with ML in general. And it also, every template that we provide there also is associated with the data set that is used to train that model. So that, to me, I would recommend that as a great starting point. Let me see. At which instances would it be better to use the scanner API as opposed to an ML classifier? It really depends on your use case. I mean, the scanner one is great if you want to like localize and kind of like get some more robust models that are coming out of it. If you want to train your own ML classifier on something that is for which the class is not already provided, then we also recommend the ML classifier. Is there any tutorials on how to modify the model for adding new classes or looking for other animals? The GitHub repository that I shared is actually a great way to be able to do that, because with some of the starter ML models that we provide, it's only a matter of just like swapping out the different classes and also just inputting in a new data set to work with it. Do we need any coding knowledge for starting this? We recommend having some Python knowledge to get started with it. If you just want to, just use kind of like the similar model architecture that we've already provided, then it's mostly a case of just navigating the notebook to be able to swap the data set and also just tweak the model a little bit. So some Python knowledge is definitely necessary there. But if you want to go to the next level of like training your own ML model and configuring it the way that you care about, then we recommend having some sort of starter knowledge and machine learning frameworks such as PyTorch, and maybe taking an intro to machine learning class online. Eric, do you want to take the next question from David, I believe, in a live video setting?
Sorry, let me take a look. Yes, so we are able to control the frequency at which the model runs. I think in Lens Studio, we have the option to set to run the model for every frame or just at each frequencies. I think let me try to find if I can find the exact API that controls this, but it's doable inside Lens Studio.
And to follow up on Pam's question, so would it be just a low probability? Yes, I mean, the idea is that you can actually tweak the probability thresholds for something to become a class of other or a cat or versus dog. So that's something that you can actually configure in the model as you're setting up the parameters. Will Onyx models from apps like Lope.ai be supported? I am not sure about that one. Maybe we can take a look at this after the session and we can get back to you, Ines. Tutorial +1 to tutorial on how to modify an existing model and Google setup. So this will, as I said, we'll be sharing this specific notebook with you guys. So that should hopefully solve some of those questions. But if there's more walkthroughs and tutorials that you need, please send those requests to us. We're more than happy to work with you to make something like that happen. Prerequisite to getting started. I believe I answered that question a little bit. Custom action classifier models compatible to recognize poses and classify them. So we do have the body tracking capabilities in Lens Studio. So that I recommend kind of taking a look at that and seeing what you can do with the pose components there. And then if I guess like it doesn't meet what you're expecting, then you would then classify or build and train a model to identify specific poses that you care about, and then you can use SnapML for that. I don't believe we currently have a notebook on SnapML that does that specifically, but again, if there is interest in it, we're more than happy to take a look. Sometimes a chair gets recognized as a human in Lens Studio. Do we have an option to increase the tolerance? If you're talking about a SnapML model, I mean, if that is the case, then usually retraining that model and providing it better data sets could be a great first step to looking into it. Can I ask about other templates, or is this only for the object recognition one? We have plenty of templates to get started. So if you go into our SnapML Lens Studio documentation, you'll be able to take a look at all of the templates that we provide. And then the GitHub repo link that I shared includes training code for other machine learning use cases, such as classification, object detection, style transfer, and more. Is there an ML component for trained voice detection model? So the input to be voice. So we do have a voice ML component in Lens Studio, and then we also have an audio ML component. So I recommend you can take a look there for your use case. Is it possible to get class names when using object detection, or do we only get location and probability scores? So if I'm not sure I'm understanding this question correctly, so I guess I'll try to cover it as much as I can. And Eric, feel free to jump in here. But as far as I understand, yes, you should be able to get the class names when you're using object detection. Right, Eric?
Yeah, I think for now, the only template we released for object detection is a single class object detection. So
yeah,
we don't, so there's not like, it doesn't matter if we get class names or not, but we were planning to release a multi-object detection template. In that template, we definitely were like able to get class names, bounding boxes, and scores.
Mm-hmm. Eric, do you want to take Tim's question as well?
Basically, we're using SnapML human model for trial, but sometimes the C case gets stressed, which should only trigger the model if 90% confident it's human. So is that a setting for that? So we're looking into this model. Ideally, yes, it's doable in Lens Studio. So we talk to the creators for this template and see how we can improve on this. Thanks for the feedback.
Mm-hmm. And then Alvaro, you have a question around the add beard model. You've tested it, it looks great, but not customizable at all. Do we have to make a new model for changing the shape of the beard or something like that? Yeah, and I think, Eric, correct me if I'm wrong, I don't think we have a training code or a training model for the add beard template. So that would essentially mean that you would probably want to take a look at making a new model if you want to, I guess, like customize or change that model altogether. I'm gonna go quickly into the Q&A section because I think that there's a few more questions there. I think, David, we already answered your question on the frequency and the scanner API. Ines will be following up with you on the Onyx model for Lobe. And then there's also another question from Ines. Have tried these apps and created Onyx files, but none of them got accepted into Lens Studio. Again, I believe this has to do with Lobe AI and a bunch of other websites. So Ines, just as a high level, and I'm more than happy to follow up with you on this. Like, as I mentioned a little bit in the presentation, there's a little bit of configuration that has to go into the Onyx files before they get inputted into Lens Studio. So it might just be a question of kind of like identifying the right components that we need to make these files work on Lens Studio. So we'll reach out to you and we'll take it from here. All right. Yes, we will be sharing the presentation material and everything. We'll also follow up on the recording. Hopefully we'll be able to find something a little bit more high quality for you folks. All right. I don't see any more questions. So thank you, everybody, again, for being here today. And if you have any more follow-up questions, I'm sure the folks in the team will make sure to redirect those to us and we'll take care of it for you. Really appreciate it again.